All right, welcome. Today, we are diving deep into what might just be the next huge leap in wireless technology, terahertz communication. It's a total game changer, and we're going to break down what it is, why it's so darn difficult to pull off, and the really clever ways engineers are making it happen.
But first, I want you to just think about something for a second. Forget your current Wi-Fi. Forget 5G. What if everything you do online, downloads, streaming, gaming, all of it, was over 100 times faster than anything you've ever experienced? Seriously, that's the world we're about to step into. We're talking about a target speed of 1 terabit per second. That's 1,000 gigabits. I mean, to put that into perspective, you could download hundreds of high-def movies in like the time it takes you to blink. It's a speed that sounds almost fake, right? But it's the very real finish line for THD communication.
Okay, so why all the effort? To really get why researchers are pouring so much into this, we have to look at what it actually makes possible. Let's explore what's being called the terahertz dream.
So why is this such a big deal? Well, for starters, the terahertz band is this massive, wide-open frontier of radio waves that we haven't even touched yet. It's like a brand new, empty superhighway for data. All that space means we can finally do things that, have felt like science fiction. We're talking real holographic calls, a metaverse that's actually immersive and has zero lag, and robotic systems that can react instantly. And get this, because the waves are so tiny, it lets us sense and position things with millimeter-level accuracy. It's wild. But if this stuff is so incredible, why isn't it everywhere already? Well, this is where the reality check comes in. The thing about a terahertz signal is that it's this weird paradox. It's incredibly powerful in what it can do, but it's also unbelievably fragile in the real world. And that's really the core problem we have to solve.
And this table really lays out that paradox perfectly. On the one hand, you have all this amazing untapped bandwidth. The signals are narrow, which makes them really secure. That's the good news. The bad news? These signals suffer from what's called severe path loss. They just run out of steam incredibly fast, and they can get blocked by anything: walls, rain, even just the water vapor in the air.
So let's meet the two main villains of our story. First up is severe path loss. The best way to think about it is like a flashlight. The beam is super bright right up close, but it gets really dim really fast the further away you get. That's a terahertz signal. And the second villain is molecular absorption. This is where molecules just floating in the air, especially water, literally soak up the signal's energy, stopping it dead in its tracks. So how in the world do you fight these villains? I mean, you can't just change the laws of physics, right? But what you can do is get really clever and engineer your way around the problem. So let's open up the engineer's toolkit and see what kind of solutions they've come up with.
Our first tool is a technology you might have already heard about from 5G, but this is like MIMO on steroids. It's called multiple input, multiple output, and the idea is actually pretty simple but totally brilliant. You use an army, I'm talking hundreds or even thousands, of tiny little antennas, all working together to create one single, super powerful and highly focused beam of data.
And you can see the difference right away. Before MIMO, you've got this weak signal that just kind of scatters and fades out. But with MIMO, all those antennas pool their energy together. It's like taking a dim light bulb and focusing it into a powerful laser beam of data. This directly fights back against that path loss problem.
Okay, so a laser beam of data is great, but what happens when there's a big solid wall in the way? That's where our next tool comes in. It's called a reconfigurable intelligent surface, or RIS, and the easiest way to think of it is like a smart mirror for radio waves. It's a surface you can program to catch a signal and bounce it exactly where you want it to go.
And the impact here is just obvious. On the left, the signal hits the wall. Game over. It's blocked. But on the right, you put an RIS on another wall, and it catches that signal and just intelligently bounces it right around the corner. All of a sudden, you have a connection that should be physically impossible. This is absolutely critical if we want to make THZ work indoors.
Now, all this sounds fantastic. We've got MIMO, we've got these smart surfaces. Problem solved, right? Well, not so fast. Because in the world of engineering, there's no such thing as a free lunch. Every single choice, every solution comes with a complicated trade-off. Just take beamforming. That's the technique for steering the signal. You can do it digitally, which is incredibly flexible and powerful. You can send multiple streams of data. It's amazing. But it's super complex and it eats a ton of power. Or you could do it with simpler analog parts. That's much more power efficient, but it's way less capable. It's that classic dilemma. Do you want raw performance or do you want something that's efficient and simple?
And it's never a one-size-fits-all solution. Think about how you actually encode the data onto the signal. If you're in a speeding car, the signal gets distorted by the speed. That's the Doppler effect. For that environment, you need a specific method called OTFS. But if you're in a crowded room where the signal is bouncing off of everything, total chaos, a completely different method called OFDM works better. You have to pick the right tool for the job.
This whole balancing act gets even more intense when the system has to multitask. Remember that awesome millimeter-level sensing we talked about? Well, you can use the same signal for both sensing and communication, but you have to choose how to split the bandwidth. Do you want better sensing? Okay, you get amazing precision, but your data speed goes down. Or do you want maximum download speed? Great, but your sensing won't be as accurate. It's a constant negotiation inside the system itself.
So we've seen the incredible potential. We know the huge challenges, and we have this whole toolkit of really clever solutions. So where does Terahertz technology actually stand today? What's the road ahead look like?
While we are definitely making progress, there's already an official standard that can handle up to 100 gigabits per second, which is amazing. And in the labs, we're seeing huge breakthroughs in the actual hardware needed to make it all work. But that final step, getting it out into the real world, that all depends on clearing the last major hurdles, making the hardware mature, reliable, and cheap enough for everybody.
And that brings us to what's probably the most honest summary of where we are right now. And this comes directly from the research. The key components are, and I quote, immature and costly. Basically, we've figured out most of the science. The real challenge now is the engineering and manufacturing, actually building the stuff at scale.
Okay, so let's tie this all together. The big takeaway here is that 1. THZ promises a truly revolutionary jump in what wireless can do. 2. This power is really fragile and faces huge roadblocks like path loss. 3. Engineers have a smart toolkit with things like MIMO and RIS to fight back. 4. Every single one of those solutions is a complex trade-off. And finally, the future is incredibly close, but the last barriers are cost and just getting the hardware ready for prime time.
Which really leaves us with one final thought to chew on. This technology isn't a question of if anymore, it's a question of when. It's right around the corner. So the real question is, when it finally gets here, are we actually ready for the kind of instant, seamless, and immersive world that it's going to create? Thanks for watching.